Did you know the universe is far more connected than we ever imagined? Out there, beyond the scattered stars and swirling galaxies, lies an invisible cosmic architecture, a vast, delicate network stretching across billions of light years, binding everything together in a web so colossal it defies comprehension. This is the cosmic web, the hidden skeleton of the universe, and what you're about to discover will change how you see the cosmos forever. Think of it like this: if the universe were a living organism, the cosmic web would be its nervous system, threading through the emptiness, whispering secrets about how everything, from the tiniest atoms to the grandest galaxy clusters, is intertwined in ways we're only beginning to understand. But here's what's truly mind-blowing. For most of human history, we had no idea this structure even existed. The stars we see at night, they're just the glittering surface of something far deeper, far stranger. The cosmic web is made of dark matter, ghostly filaments of gas, and galaxies strung like beads on an invisible string, forming a pattern so immense it takes supercomputers to even begin mapping it. And yet, despite its scale, it's remained one of the universe's best-kept secrets until now. That's where this journey begins. Over the next 30 revelations, we'll pull back the curtain on the cosmic web's greatest mysteries: how it shapes the birth of stars, why it holds clues to the fate of the universe, and what it tells us about forces so powerful they bend space itself. You'll witness the moments when scientists first glimpse this hidden structure, the mind-bending theories that explain its origins, and the jaw-dropping evidence that proves we're all part of something far grander than we ever dreamed. So buckle up, because by the time we're done, you won't just see the night sky the same way again. You'll feel it. The universe isn't just out there, it's all around us, woven into the very fabric of existence. And the story starts now. The first secret is the most humbling: everything we see in the night sky, every star, every galaxy, is just floating on an invisible scaffold. Imagine looking at a city skyline at night, glowing with lights, but never realizing those buildings are all connected by hidden steel beams beneath the surface. That's the cosmic web. Its backbone isn't made of stars or gas. It's woven from something far more mysterious: dark matter. Now, dark matter doesn't glow, reflect, or interact with light at all. We can't see it, touch it, or even detect it directly, but we know it's there because of the way it tugs on everything around it with gravity. Picture throwing glitter onto a spiderweb. You wouldn't see the web itself, but the way the glitter clings reveals the shape. Galaxies are like that glitter, tracing out these vast, sprawling filaments of dark matter stretching across the universe. Some of these threads are hundreds of millions of light years long, thin as wisps of smoke, and yet they hold entire clusters of galaxies in their grasp. Scientists first pieced this together by staring deep into the cosmos, mapping thousands of galaxies and noticing something eerie: they weren't scattered randomly. Instead, they lined up along strange, interconnected pathways like beads on a string. Supercomputer simulations showed why. Dark matter's gravity pulls matter into these vast, winding rivers, creating a cosmic skeleton. The galaxies we see are just the bright decorations hanging from its unseen framework. What's even wilder, without these filaments, the universe as we know it wouldn't exist. They funnel gas into dense pockets, igniting the birth of stars. They dictate where galaxies cluster and how they move. They're the reason the cosmos isn't just a blank, empty void, but a dynamic, woven tapestry of light and shadow. And yet, for something so fundamental, it took us until the late 20th century to even suspect it was there. That's the irony of the cosmic web. It's the most dominant structure in the universe, and yet, without the right tools, it's completely invisible to us. Like standing in a forest and suddenly realizing every tree, every leaf, is connected by a hidden root system beneath your feet. The universe isn't just out there. It's all tied together, every piece linked by threads we're only now learning to trace. If those dark matter filaments are the universe's hidden scaffolding, Then galaxies are the jewels strung along them, gleaming cities of stars drawn together by gravity's relentless pull. Picture a necklace scattered across a table, its beads sliding into place along the chain, clustering where the links bend and knot. That's exactly how galaxies behave on the grandest scale. They don't drift aimlessly, they gather where the cosmic web's filaments intersect, piling up like cosmic traffic jams at gravity's busiest intersections. One of the most staggering examples is the Sloan Great Wall, a filament so colossal it defies belief. Stretching nearly 1.5 billion light-years across, it's one of the largest known structures in the universe, a serpentine ribbon woven with thousands of galaxies. To grasp its scale, imagine a highway so long it would take light, the fastest thing in existence, over 1 billion years to travel from one end to the other. And yet, what's truly astonishing isn't just its size, but how perfectly it illustrates gravity's handiwork. Over billions of years, the gentle tug of dark matter pulled gas and dust into these threads, and galaxies bloomed where the density was highest, like flowers sprouting along a riverbank. But here's where it gets even stranger. Gravity doesn't just arrange galaxies, it orchestrates their dance. Within these dense knots, galaxies don't sit still. They whirl around one another, sometimes colliding in spectacular mergers that trigger bursts of new stars. The Milky Way itself is part of a filament, part of a local supercluster, moving toward an even more massive, not known as the Great Attractor, a gravitational anomaly so powerful it's pulling thousands of galaxies toward it, like a cosmic whirlpool we can't escape. Yet for all their grandeur, these galactic beads on a string reveal a deeper truth. The cosmic web isn't static. It's alive with motion, a dynamic network where gravity sculpts the universe in real time. Every galaxy cluster, every filament, is a snapshot of an eternal process, one that began with the faintest whispers of density in the early universe and grew, over eons, into the structures we see today. And just as the web shaped the galaxies in turn shape the web. Their gravity pulls on the dark matter, their light reveals its contours, and their very existence helps us unravel the universe's grand design. To understand how the cosmic web came to be, we have to rewind time way back to a fraction of a second after the Big Bang. Back then, the universe wasn't filled with galaxies or dark matter filaments. It was a searing hot soup of particles, so dense and chaotic that even light couldn't escape. But hidden in that primordial chaos were tiny ripples, quantum fluctuations so small you'd need a microscope to see them if such a thing existed back then. These weren't just random blips, they were cosmic seeds, the blueprints for everything we see today. Here's the incredible part: those microscopic ripples held the faintest variations in density, little pockets where matter was ever so slightly more crowded. And over billions of years, gravity got to work. Like a sculptor shaping clay, it took those subtle differences and amplified them. The denser regions pulled in more matter, growing heavier, while the emptier spaces stretched thinner. What started as faint whispers in the fabric of space-time gradually became the vast filaments and voids we recognize now. Think of it like blowing up a balloon with tiny dots drawn on it. As the balloon expands, the dots don't just get farther apart. They form patterns, clusters, and lines based on where they started. The cosmic web works the same way. Those initial quantum ripples set the stage, and the expansion of the universe stretched them into the grand structure we see today. But gravity didn't just stretch these threads, it braided them. Dark matter, invisible and relentless, acted like an unseen hand, pulling matter into its grip. Ordinary gas and dust followed, flowing along these dark highways, pooling at the intersections where galaxies would eventually ignite. It's a process so slow and precise that even now, billions of years later, we can still trace its fingerprints in the way galaxies align, like echoes of that first cosmic whisper. What's truly humbling is realizing we're seeing a snapshot of a process still unfolding. The cosmic web isn't finished. It's still growing, still evolving, as new threads form and old ones stretch further into the void. And those same quantum ripples that birthed it, they're still out there, etched into the afterglow of the Big Bang, waiting for us to decode their secrets. Dark energy is the universe's ultimate wildcard, an invisible force so powerful it's stretching the cosmic web apart, thread by thread. Picture a tug-of-war where gravity pulls galaxies together, weaving them into filaments, while dark energy does the opposite, yanking the universe outward with unstoppable force. This cosmic battle didn't always exist. For billions of years, gravity had the upper hand, patiently assembling the web's intricate structure. But then, around 5 billion years ago, something flipped. Dark energy took over, and the universe's expansion began to accelerate, as if space itself had stepped on the gas. The eerie part, dark energy isn't pulling on the cosmic web, it's stretching the very fabric it's built on. Imagine a spiderweb glued to two branches. If you slowly move the branches apart, the web's threads grow thinner, some snapping under the strain. That's exactly what's happening on a cosmic scale. The voids between filaments are widening, and the threads themselves are growing fainter as galaxies at the edges get dragged away from one another. Over time, this could leave the web's structure isolated, like islands drifting in an ever-expanding sea of nothingness. Yet gravity refuses to surrender entirely. In the densest knots of the web where galaxies cluster tightly, its grip is still strong enough to resist dark energy's pull, at least for now. Places like the Laniakea supercluster, home to the Milky Way, are holding their shape, their colossal mass creating gravitational anchors in the cosmic tide. But even these fortresses may not last forever. Simulations suggest that trillions of years from now, dark energy could stretch space so much that distant galaxies will vanish from view, their light stretched beyond detection. The cosmic web, once a bustling network, might become a ghostly relic of a more connected universe. What's baffling is that we still don't know what dark energy actually is. Is it a property of space itself, or some unknown particle humming through the void? All we know is that it's winning the tug-of-war, reshaping the universe in ways we're only beginning to fathom. And just as gravity's fingerprints are etched into the web's design, dark energy's influence is there too in the growing voids, the thinning filaments, and the silent, relentless expansion of the cosmos. One force builds, the other unravels, and caught between them is the delicate, ever-changing architecture of everything. For decades, astronomers faced a cosmic detective story with a baffling lead. Half the universe's ordinary matter had simply vanished. We're not talking about dark matter here, but the stuff we're made of: protons, neutrons, the atoms that build stars, planets, and us. Math told us it had to exist, yet when scientists tallied up all the visible galaxies, gas clouds, and dust, nearly half was missing. The answer to this mystery wasn't lurking in some distant corner of space. It was hiding in plain sight, woven into the very fabric of the cosmic web. The breakthrough came when researchers trained X-ray telescopes like Chandra on the faint threads between galaxies. There, they found a searing hot, whisper-thin fog of gas, superheated to millions of degrees and stretched into filaments so diffuse they're practically invisible to optical telescopes. This wasn't just any gas, it was the elusive missing baryonic matter hiding in the web's delicate strands all along. Imagine trying to spot a fog bank at night from a mile away. To your eyes, it might seem like empty darkness, but shine a spotlight through it, and suddenly the hidden moisture glows. That's exactly how X-ray telescopes revealed the cosmic web's hidden gas. When light from distant quasars passed through these filaments, the hot gas absorbed specific wavelengths, leaving fingerprints in the spectrum. And when Chandra observed massive galaxy clusters, it detected a faint X-ray glow, the telltale sign of this superheated plasma, swirling like steam around the web's densest knots. The sheer scale of this discovery is staggering. This hidden gas isn't just a trace, it accounts for nearly all the universe's missing ordinary matter, a reservoir so vast it outweighs all the stars in existence by a factor of 10. Yet it's so thinly spread that a cubic meter of this intergalactic fog might hold just a few hundred atoms. A vacuum by Earth standards, but when stretched across billions of light years, it adds up to the universe's biggest stockpile of raw material. What's even more fascinating is how this gas got so hot. As the cosmic web formed, gravity didn't just pull matter into filaments, it sent shockwaves rippling through them like cosmic sonic booms. These waves compressed and heated the gas, turning it into a high-energy plasma too faint to see directly but impossible to ignore once we knew where to look. And now, this discovery is rewriting textbooks. The galaxies we marvel at aren't isolated islands, they're nodes in a vast, hot river system, fed by streams of ionized gas that flow along the web's invisible channels. The missing baryons weren't lost after all. They were just waiting for us to look in the right way with the right tools, revealing once again that the universe's greatest secrets often lie not in the glaringly obvious but in the spaces between. If the cosmic web is a labyrinth of glowing threads and glittering galaxy clusters, then the voids between them are its shadowy chambers, vast, echoing spaces so empty they defy intuition. These aren't just gaps, they're cosmic deserts, some stretching over 300 million light-years across, where galaxies are almost entirely absent. Picture a balloon inflating to the size of a city, with a few scattered grains of sand inside. That's the scale of emptiness we're talking about. What's astonishing isn't just their size, but how they shape the universe's structure. While filaments pull matter together, voids push it away, acting like cosmic repellers. Imagine blowing on a dandelion, the seeds flee from your breath, just as galaxies near a void's edge are gently nudged outward by its expansion. This creates a bizarre paradox. The emptiest places in the cosmos are somehow actively shaping where matter goes. Scientists first grasped the enormity of voids by mapping thousands of galaxies and noticing eerie, bubble-like patterns. The Boötes void, one of the largest ever found, is so sparse that if you placed the Milky Way at its center, our nearest galactic neighbor would be almost unimaginably distant. Yet these voids aren't completely barren. Scattered within them are rebel galaxies, lonely outcasts that somehow resisted the pull of the web. Some drift like ghosts, their stars burning faintly in the darkness, while others may hold clues to how structures form in the most extreme environments. But here's the real twist. Voids aren't passive holes. They're dynamic engines, their emptiness warping the very fabric of space-time. Light passing through a void travels slightly faster than through crowded regions, a quirk of gravity's absence that bends our view of distant objects like a funhouse mirror. Even stranger, the universe's expansion accelerates slightly faster inside voids, as if dark energy finds less resistance there. It's a reminder that emptiness isn't just nothingness. It's a force with its own rules, its own influence, quietly sculpting the cosmos in ways we're only beginning to measure. The more we study these voids, the more they upend expectations. They shouldn't exist in such sizes according to early universe models, yet here they are, gaping cosmic anomalies that challenge our grasp of how matter arranges itself. Perhaps they're fossils of the universe's infancy, regions where quantum fluctuations left nothing to grow, or maybe they're evidence of forces we haven't yet named. Either way, they're proof that the universe's grand design isn't just written in the stars, it's etched into the silence between them. The cosmic web isn't just a network of matter and dark energy. It's also threaded with invisible rivers of magnetism, forces so subtle we almost miss them entirely. For years, scientists assumed magnetic fields were confined to galaxies or galaxy clusters, localized phenomena like weather patterns on a planet, but recent breakthroughs have shattered that assumption. We now know the web's filaments are alive with magnetic fields, stretching millions of light-years like cosmic power lines, their influence quietly shaping the universe in ways we're only beginning to decode. These fields aren't just faint whispers, they're surprisingly strong. Imagine a bar magnet the size of a galaxy cluster. then stretch its pull across a void so vast it could swallow 1,000 Milky Ways. That's the scale we're dealing with. Researchers detected these fields by studying the light from distant quasars as it passed through the web's filaments. When the light arrived, its polarization, the direction its waves vibrated, had subtly shifted, as if twisted by an unseen hand. The culprit, magnetism woven into the very fabric of the cosmic web, bending light like a lens bends a beam. What's truly mind-bending is how these fields got there in the first place. One theory suggests they're ancient relics, born in the chaos of the early universe when plasma currents flowed like rivers, generating magnetism that never fully faded. Another possibility is that they're the work of supermassive black holes, their jets pumping magnetic energy into intergalactic space like cosmic fire hoses. Wherever they came from, their impact is undeniable. These fields act as cosmic highways for high-energy particles, steering cosmic rays, the universe's fastest, most energetic particles along the web's filaments. Without them, these rays might scatter randomly, lost in the void. Instead, they're funneled efficiently, potentially delivering the energy needed to spark star formation in distant galaxies. But magnetism's role doesn't stop there. These fields may also solve one of astrophysics' lingering puzzles: why some galaxies spin faster than gravity alone can explain. The answer could lie in magnetic tension, an invisible force gripping gas clouds, adding torque to their rotation like a hand twisting a rope. And when galaxies collide, their magnetic fields tangle and amplify, creating shock waves that ignite new stars or even power quasars, the universe's brightest beacons. The more we learn, the clearer it becomes. Magnetism isn't just a side effect of the cosmic web. It's a foundational force, as vital to its structure as gravity or dark matter. Like a symphony's hidden harmonies, these fields don't announce themselves loudly, but without them, the music of the universe would sound entirely different. And with every new discovery, we're tuning into frequencies we never knew existed. Some structures in the cosmos are so immense they make galaxies look like specks of dust, and the Hercules Corona Borealis Great Wall is one of them. Stretching an almost inconceivable 10 billion light-years across, this filament complex isn't just big, it's a cosmic anomaly, a thread so vast it throws our understanding of the universe's limits into question. To put that in perspective, if you could travel at the speed of light, it would take you longer to cross this single structure than the Earth has existed. That's not just a record breaker, it's a potential rule breaker, challenging one of astronomy's most fundamental assumptions, the cosmological principle. This principle states that, on large enough scales, the universe should look roughly the same in every direction, no glaring irregularities, no patches noticeably denser or emptier than others. It's the backbone of modern cosmology, the reason we can apply the same physics to distant galaxies as we do to our own neighborhood. But the Hercules Corona Borealis Great Wall tests that idea to its limits. Here's why. Based on our current models of how matter clumps together, a structure this massive simply shouldn't exist. It's like finding a single mountain range stretching across half the Earth, possible, perhaps, but defying everything we know about how mountains form. The discovery came when astronomers mapped gamma-ray bursts, the universe's most violent explosions across the sky. These fleeting flashes aren't random, they trace the densest regions of galaxies, acting like cosmic breadcrumbs. When researchers connected the dots, a staggering pattern emerged. An enormous concentration of bursts spanning nearly a seventh of the observable universe. This wasn't just a cluster of galaxies, it was a sprawling superstructure, a cosmic continent where galaxies, gas, and dark matter weave together on a scale that redefines big. Yet its existence isn't the only puzzle. The Great Wall's sheer size hints that either our models of cosmic evolution are missing something fundamental, or the universe isn't as uniform as we thought. Some theorists argue it could be evidence of exotic physics, perhaps primordial energy fields from the Big Bang imprinting megastructures into space-time itself. Others suggest it's not a single structure at all, but multiple filaments viewed in a way that creates an illusion of connectedness, like seeing separate mountain peaks aligned by chance from a distance. What's undeniable is how this colossal web of galaxies forces us to reconsider the universe's architecture. If structures this vast can exist, what else might be out there lurking in the darkness? Are we seeing a flaw in our theories or a sign that the cosmos is far stranger, far more varied than we ever imagined? The Hercules Corona Borealis Great Wall doesn't just stretch across space, it stretches our minds, reminding us that the universe's grandest designs are still waiting to be unraveled. The cosmic web isn't just a passive scaffold, it's a dynamic delivery system, channeling the raw materials of creation straight into the hearts of hungry galaxies. Picture a network of rivers flowing through a desert, their waters feeding oases where life blossoms. That's exactly how the web's filaments work, but on a scale so vast it bends the imagination. These invisible highways of dark matter don't just arrange galaxies, they feed them, funneling hydrogen gas into cosmic nurseries where stars ignite like fireworks in the dark. Here's how it happens. Gravity, the universe's great architect, pulls gas along these filaments like water sliding down a slope. But it's not a smooth, steady flow, it's a chaotic cascade. When streams of gas collide at the intersections of filaments, they pile up in dense knots, creating reservoirs of material so rich they can spawn millions of stars at once. Think of it like traffic merging on a highway. The slower-moving gas gets compressed, heated, and eventually collapses under its own weight, sparking the birth of new stellar fire. Some of the most stunning evidence comes from the edges of young galaxies, where telescopes like ALMA have spotted tendrils of gas spiraling inward, pulled by gravity's relentless tug. These aren't gentle drips, they're torrents, sometimes delivering enough material to double a galaxy's star-forming fuel in just a few 100 million years. And the web doesn't discriminate. Even the smallest galaxies, perched like dewdrops on the filaments, get their share, growing steadily as gas trickles in from the cosmic tributaries around them. But the web's role doesn't end there. These rivers of gas don't just feed galaxies, they shape them. When inflows are turbulent, they can trigger bursts of star formation, lighting up galactic disks like neon signs. Too much gas too quickly, though, and the result is chaos, galactic collisions, runaway star birth, or even the awakening of supermassive black holes that blast away excess material in fiery jets. It's a delicate balancing act, one that's played out over billions of years, with the web's filaments as both the stage and the script. What's truly remarkable is how efficient this system is. Without these cosmic pipelines, galaxies would starve, their star-forming gas scattered too thin to ignite. Instead, the web ensures that even the most remote corners of the universe get their share of building blocks, weaving a tapestry of light across the void. And just as rivers carve canyons over time, these filaments leave their mark, imprinting galaxies with distinct chemical signatures, twisted spiral arms, and even the orbits of their stars. So the next time you gaze at a galaxy spinning in the night, remember, it's not just an island in space, it's the product of an ancient, invisible river system, one that's been flowing since the dawn of time, delivering the gift of creation thread by thread. Long before the first stars flickered to life, the universe was a silent sea of darkness but not emptiness. Within that primordial gloom, hydrogen atoms whispered secrets in a language older than light itself. These whispers weren't sound, but faint radio signals, echoes from a time when the cosmic web was just beginning to take shape. Today, astronomers are tuning into these ancient frequencies, peeling back layers of time to reveal how the universe's largest structure emerged from the chaos of its infancy. The key lies in a phenomenon called the 21-centimeter line. When hydrogen atoms, the universe's most abundant element, shift their electron spins, they emit a subtle radio wave at this precise wavelength. In the early cosmos, before stars polluted space with light, these signals rippled freely, painting an invisible map of where gas clustered and where voids stretched wide. Imagine an artist sketching with invisible ink, their brushstrokes only revealed under black light. That's what cutting-edge telescopes like the Square Kilometre Array and the Low Frequency Array are doing, illuminating the cosmic web's faint blueprint in radio waves we've only just learned to decipher. But catching these whispers isn't easy. 13 billion years of cosmic expansion have stretched those original 21-centimeter signals into meter-long waves, as faint as a candle flickering on the moon. To detect them, scientists must sift through a cacophony of radio interference, everything from Earth cell phones to distant pulsars, like trying to hear a pin drop in a thunderstorm. Yet the payoff is immense. These signals don't just show where early gas collected. They reveal how it moved, how gravity's unseen hand sculpted the first filaments, and how the web's architecture guided the birth of galaxies. Recent breakthroughs have given us tantalizing glimpses. When researchers trained the Murchison Widefield Array on a patch of sky for thousands of hours, they detected a diffuse glow not from stars, but from hydrogen gas woven into filaments during the universe's dark ages before starlight pierced the gloom. The pattern matched supercomputer simulations of the web's infancy, proving that its skeleton existed long before the galaxies that now decorate it. What's even more astonishing is how these signals betray the web's temperature. In regions where gas pooled along filaments, collisions between atoms heated the hydrogen, subtly altering its radio signature. Where voids formed, the gas cooled, its whispers fading into colder, quieter tones. These thermal fingerprints let scientists reconstruct cosmic weather maps from an era when the universe was less than 1 billion years old, a forensic snapshot of gravity's earliest handiwork. The next generation of radio telescopes promises to sharpen this picture exponentially. Projects like the Hydrogen Epoch of Reionization Array aim to trace the web's evolution as the first stars ignited, their ultraviolet radiation frying the surrounding hydrogen like a cosmic flash fry, stripping electrons and silencing the 21-centimeter whispers forever. By mapping where and when this signal vanished, we'll witness the exact moment the web transformed from a silent scaffold into a glittering stage for galaxies, a revolution written in radio waves, waiting for us to listen. These whispers from the dawn of time aren't just relics. They're a direct line to the universe's formative years, proving that even in the darkness before stars, the cosmic web was already there, quietly knitting itself together, one hydrogen atom at a time. And now, at last, we're learning its language. At the heart of the cosmic web's busiest intersections, where filaments collide in a tangle of gravity and gas, lurk the universe's most insatiable predators, supermassive black holes. These aren't just any black holes, they're cosmic engines of destruction and creation, some weighing billions of times more than our sun, hidden in the densest knots of the web. And their secret, they thrive where the rivers of gas converge, gorging on the very material that feeds galaxies, transforming serene cosmic highways into all-you-can-eat buffets of interstellar matter. Picture the web's filaments as freeways packed with hydrogen gas, all flowing toward massive interchanges, the galaxy clusters, but at these junctures something sinister waits. As gas piles up, it doesn't just form stars, it funnels toward a central point, swirling faster and faster like water down a drain. At the center of that whirlpool, space-time itself gives way, and a supermassive black hole begins its feast. The process is terrifyingly efficient. Gas doesn't just fall in, it spirals violently, heating up to millions of degrees and glowing brighter than entire galaxies before vanishing beyond the event horizon. This isn't just theoretical. We've seen the aftermath in quasars, the brightest objects in the universe. These are nothing more than black holes in overdrive, their frenzied feasting generating jets of energy so powerful they outshine every star in their host galaxy combined. And where do we find most quasars? Nestled right where the cosmic web's filaments meet, like spiders perched at the center of their silk. The connection is undeniable. The web's structure doesn't just feed galaxies, it fuels the monsters at their cores. But here's the twist. These black holes aren't just destroyers, they're sculptors. As they devour gas, they release torrents of energy, jets of plasma moving at nearly the speed of light, punching through galaxies and beyond, heating the surrounding gas in the web's filaments. This creates a feedback loop so intense it can shut down star formation entirely, like a cosmic thermostat. Too much gas falling in, the black hole fires up, blasts the excess away, and resets the system. It's a delicate balance, one that might explain why some galaxies stop making stars long before their gas runs out. Perhaps most mind-bending of all is the scale of their influence. Some of these black holes are so massive, their gravity bends the web itself, warping the paths of nearby filaments and redirecting the flow of gas across millions of light years. They're not just inhabitants of the web, they're architects, shaping its growth with every meal. And as they grow, they leave behind signatures, ripples in space-time, X-ray echoes, even the subtle sway of orbiting stars, all clues that help us map the web's darkest, most enigmatic junctions. So the next time you hear about a distant quasar blazing across the cosmos, remember, you're not just seeing a black hole, you're witnessing the cosmic web's hidden power grid, a network of gravity and gas where the universe's most volatile giants lurk, always hungry, always shaping the night in ways we're only beginning to grasp. The cosmic web doesn't just shape galaxies and voids, it leaves ghostly fingerprints on the oldest light in the universe. Stretching your hands toward a campfire, you'll feel warmth, but also notice how your fingers cast faint shadows on the ground behind you. The web's gravitational pull does something eerily similar to the cosmic microwave background, that ancient afterglow of the Big Bang. This relic radiation, bathing the universe in a faint microwave hum, isn't perfectly uniform. Subtle variations in its temperature and polarization reveal where the web's massive filaments gently warped its path over billions of years, bending light like a prism warps sunlight. When the Planck satellite mapped the CMB in exquisite detail, it didn't just capture a baby picture of the cosmos, it caught the web red-handed, the telltale signs. Slight temperature dips where CMB photons lost energy climbing out of the web's deepest gravitational wells, and subtle twists in the light's polarization where filaments acted like cosmic funhouse mirrors. These distortions, known as the integrated Sachs-Wolf and gravitational lensing effects, are vanishingly faint, less than a millionth of a degree, but they form a sprawling, whisper-thin blueprint of dark matter's hidden architecture. The most striking validation came when scientists compared Planck's CMB maps with galaxy surveys like the Sloan Digital Sky Survey. The patterns matched. Regions where the CMB showed slight dimming aligned perfectly with superclusters, while brighter patches mirrored vast voids. It was as if the universe had pressed its fingerprint onto the CMB, leaving behind a forensic trace of the web's growth. Even more remarkable, these imprints aren't static. They're snapshots of the web's evolution, the gravitational echoes of filaments growing denser as dark energy pushes matter into ever sharper relief. But the web's fingerprints aren't just about gravity's pull. They also encode secrets about the universe's expansion. When CMB photons traverse a filament, the stretching of space itself slightly shifts their wavelength, a phenomenon called the Rees-Simon effect. This creates a distinctive pattern, cold spots where photons expended energy entering overdense regions, and warm spots where they gained energy racing away. It's a cosmic Doppler effect, and it reveals how the web isn't just a structure but an active participant in spacetime's dance. What's breathtaking is how delicate these signals are. Detecting them required Planck's instruments to measure temperature variations smaller than 1 part in 100,000, like discerning a single snowflake's weight on a mountain. Yet that precision unveiled a profound truth. The cosmic web isn't just a bystander in cosmic history. It's a sculptor etching its story into the very fabric of the universe's oldest light. And with every new map, we're learning to read its handwriting. Our galaxy is caught in a cosmic current, swept toward something unseen, an immense gravitational vortex known as the Great Attractor. Like a river pulling leaves toward a waterfall, this invisible force drags the Milky Way and thousands of other galaxies toward a point in space we can't even see. Hidden behind the thick dust of our own galactic plane, this mysterious region holds the equivalent mass of tens of thousands of Milky Ways, bending space-time so fiercely it dominates the motion of everything within 500 million light-years. The discovery began with a peculiar pattern. When astronomers mapped galaxy movements in the 1970s, they noticed something disturbing. Entire clusters were streaming toward the same patch of sky near the constellations Centaurus and Norma. Not just drifting, but racing at over 600 kilometers per second, as if the universe had tilted downhill in that direction. The culprit, a gravitational anomaly so colossal it warps the fabric of the cosmic web itself, tugging the entire Laniakea supercluster, our galactic neighborhood, toward its grasp. Here's what makes it so strange. Normally, we'd expect such a massive attractor to glow with the light of countless galaxies. But when telescopes like NASA Chandra turned their gaze toward it, they found only partial answers. A handful of galaxy clusters like Norma Cluster, massive but nowhere near enough to explain the pull. The rest was shrouded in darkness, obscured by the Milky Way's own interstellar dust. Using infrared and X-ray eyes, we've since peeled back some of that veil, revealing more clusters and superclusters lurking behind the cosmic curtain. Yet even combined, their mass falls short, which means something else, something unseen, must be amplifying the attraction. One theory points to dark matter. The cosmic web's filaments converge here, funneling unimaginable amounts of this shadowy substance into a knot so dense its gravity overpowers everything nearby. Another possibility, the Great Attractor isn't the destination at all, but a waypoint, a stepping stone on our path toward an even larger structure, like the Shapley supercluster, a behemoth 650 million light-years away. Some simulations suggest we're caught in a cosmic tug-of-war between these titans, with the web's filaments acting as the ropes. But the most haunting idea is this: the Great Attractor might not be unusual at all. What if every supercluster has a gravitational anchor hidden in the web's densest nodes, invisible from certain angles until you're close enough to feel its pull? We're like sailors sensing a distant whirlpool by the way it bends the current, knowing that by the time we see it, escape might already be impossible. One thing's certain: as the web's filaments guide us forward, they're writing our galactic future. In billions of years, the Milky Way will arrive at the attractor's heart, merging with countless other galaxies in a collision so vast it will reshape the local universe. Until then, this unseen force remains a reminder: the cosmic web isn't just a map of where things are. It's a script of where they're going, and we're all just following its currents. At the smallest scales of existence, particles can become entangled, instantly mirroring each other's states no matter how far apart they drift. Now, imagine that same spooky connection writ large, woven into the very fabric of the cosmic web. Some physicists propose an electrifying idea. What if the universe's largest structures aren't just shaped by gravity, but by quantum bonds older than time itself? This isn't science fiction. It's a radical theory suggesting that entanglement, the same phenomenon that baffled Einstein, might have left its fingerprints on the cosmic architecture we see today. The hypothesis hinges on a staggering possibility that the early universe's quantum fluctuations, those seeds of the cosmic web, were entangled from the moment they emerged. Picture two dice rolled simultaneously in separate galaxies, always landing on matching numbers despite never communicating. If particles in those primordial density variations were linked this way, their synchronized behavior could have sculpted the web's filaments into eerily correlated patterns. Supercomputer simulations lend eerie support. When researchers modeled entangled quantum fields in the infant cosmos, the resulting large-scale structure bore uncanny resemblance to today's observed galaxy distributions. But the rabbit hole goes deeper. A handful of theorists take this further, suggesting the cosmic web might be evidence of a holographic universe, a projection of quantum information encoded on a two-dimensional surface at the edge of space-time. In this wild but mathematically coherent framework, the web's three-dimensional complexity could be akin to a shadow cast by deeper, entangled data. It's like staring at a ripple-covered pond and realizing each wave's shape is dictated by vibrations on the water's surface, except here, the surface might be the universe's boundary and the ripples are galaxies. Critics argue these ideas stretch current physics to its limits. Entanglement typically unravels at macroscopic scales due to decoherence, and linking it to cosmic structures requires mechanisms we can't yet test. Yet tantalizing clues persist. Astronomers have spotted odd statistical alignments between distant galaxy clusters, correlations that defy classic inflation models but align neatly with quantum entanglement's predictions. Even the web's filamentary structure, with its intricate nodes and voids, mirrors fractal patterns seen in quantum many-body systems, hinting at a hidden unity between the smallest and largest scales of reality. Perhaps the most provocative evidence comes from black holes. The holographic principle, first proposed to solve black hole information paradoxes, suggests all data within a volume of space might be encoded at its boundary. If true, the cosmic web's vast network could be the three-dimensional screen onto which quantum information is projected. Every filament, every void, might represent entangled qubits on the universe's edge, a cosmic processor running the ultimate simulation. Whether these theories hold up or collapse under scrutiny, they reveal a profound truth. The web's mysteries can't be unraveled by studying gravity alone. The universe might not just be connected, it could be entangled, its past, present, and future woven together by threads we're only beginning to glimpse. And if that's true, then every galaxy, every atom, is part of a conversation that began at the birth of reality itself, a whisper across the cosmos saying we are all linked. Galaxies aren't just passive collectors of gas, they're cosmic fountains, spewing material back into the cosmic web in an endless cycle of creation and recycling. Picture a massive geyser erupting into the sky, its water droplets hanging suspended for a moment before raining back down to the earth. Now imagine that same process unfolding over billions of years, with galaxies blasting out torrents of gas into the web's filaments, only for that same material to eventually cool, condense, and fall back home. This isn't just a metaphor. Supercomputer simulations and cutting-edge telescope data reveal a universe where galaxies and the web are locked in a delicate, rhythmic exchange, one that shapes everything from star formation to the very structure of the cosmos itself. The cycle begins in the hearts of galaxies where violence reigns. Supernova explosions, the deaths of massive stars, rip through interstellar gas like shockwaves, hurling it outward at thousands of kilometers per second. Meanwhile, supermassive black holes add to the chaos, their jets and radiation blasting nearby gas clear out of galactic disks. But here's the twist, that ejected gas doesn't just vanish into the void. The web's filaments catch it, cradling the material in vast, diffuse reservoirs that stretch millions of light years. Like steam rising from a boiling pot, this gas lingers in the web's threads, superheated, invisible to optical telescopes, but detectable by its faint X-ray glow. Then gravity takes the wheel. Over hundreds of millions of years, the gas gradually cools, losing energy and slowing down. As its temperature drops, it begins to clump, drawn back toward the galaxies that expelled it by the same gravitational pull it once escaped. Simulations like Illustris TNG show this process in stunning detail. Ribbons of gas flowing outward in elegant arcs, pausing at the farthest edges of galactic halos, then reversing course like a cosmic boomerang. By the time it returns, it's no longer the chaotic, superheated mess it once was. its pristine fuel cool, dense, and ready to ignite a new generation of stars. This recycling isn't just a curiosity, it's a lifeline. Without it, galaxies would burn through their gas reserves in a cosmic blink, starving themselves of the raw materials needed to form stars. The Milky Way itself is part of this dance. Observations from the Hubble Space Telescope reveal clouds of gas, some with masses millions of times that of the Sun, falling back toward our galaxy after being ejected long ago. These returning rivers of material may explain why our galaxy has kept forming stars steadily for billions of years, rather than flaring out in a brief, fiery burst. But the web doesn't just return what it's given. The gas that cycles through this cosmic fountain isn't the same as when it left. Out in the filaments, it mixes with primordial material, absorbing heavier elements blown out by other galaxies. When it rains back down, it brings new ingredients: oxygen, carbon, even the building blocks of planets enriching galaxies with every orbit. In a very real sense, the carbon in your DNA, the iron in your blood, might have once traveled the vast highways of the cosmic web, riding this billion-year loop between galaxy and void. The implications are staggering. This recycling isn't just a side effect of galactic life. It's a fundamental process that governs how galaxies grow, how stars form, and even how the web itself evolves. Without these fountains, filaments might lack the density to ignite new galaxies at their intersections. Without the returning gas, the universe as we know it might be a far emptier, darker place. So the next time you gaze at the night sky, remember, you're not just looking at stars, you're witnessing a grand cosmic exchange, a rhythm as old as time, weaving the universe together one atom at a time. The cosmic web's true skeleton isn't made of galaxies or glowing gas. It's woven from something far more elusive, dark matter. But how do you map something that's utterly invisible? The answer lies in one of Einstein's most mind-bending predictions: gravitational lensing. Picture space as a vast trampoline, with massive objects like galaxies creating dips in the fabric. Now imagine rolling a marble past one of those dips. Its path would bend, deflected by the unseen curvature. That's exactly what happens to light traveling through the universe. When distant starlight passes near a dense filament of dark matter, it doesn't travel in a straight line, it warps, bending around the invisible mass like a car swerving around a hidden pothole. This subtle distortion is our Rosetta Stone for decoding the web's dark architecture. Projects like the Dark Energy Survey have turned this phenomenon into a cosmic cartography tool, scanning millions of galaxies to measure how their shapes appear subtly stretched and twisted by intervening dark matter. The result, a three-dimensional map of the universe's hidden framework, revealing filaments so massive they could swallow galaxy clusters whole, yet so diffuse they'd feel like a ghost's breath if you passed through them. One of the most stunning revelations came when researchers combined lensing data from the Hubble Space Telescope with ground-based surveys. The composite image showed dark matter filaments stretching between galaxy clusters like cosmic suspension bridges, their gravity warping the light of background galaxies into eerie, stretched arcs, a phenomenon astronomers call cosmic shear. But the Dark Energy Survey didn't stop there. By measuring lensing patterns across 1/8 of the sky, it unveiled a web far more intricate than simulations predicted. Some filaments branch like fractal trees, while others form vast, ring-like structures encircling voids. The most surprising discovery: dark matter isn't distributed smoothly along these threads. It clumps in knots at filament intersections, mirroring how galaxies cluster, but on scales 100 times larger. This granularity hints that dark matter might interact with itself in ways we don't yet understand, perhaps through unknown forces or even primordial black holes woven into the web's fabric. What's truly revolutionary is how these maps confirm a daring hypothesis. The cosmic web isn't just a backdrop for galaxies, it's the other way around. Dark matter's scaffolding came first, its gravity dictating where galaxies would bloom like flowers along a trellis. And with next-generation telescopes like the Vera Rubin Observatory poised to map lensing distortions with even sharper precision, we're on the verge of an even grander revelation, seeing not just where the web is today, but how it's evolved over billions of years. Every warped galaxy, every stretched arc of light, is a breadcrumb leading us deeper into the dark. Where are all the dwarf galaxies? For decades, astronomers faced a glaring cosmic discrepancy. Their simulations predicted vast swarms of tiny galaxies orbiting large ones like the Milky Way, yet telescopes revealed only a fraction of that number. This wasn't just a minor accounting error. It hinted at something fundamental we'd misunderstood about how galaxies form, and the answer lies in the cosmic web's hidden grip on the universe's smallest structures. The puzzle starts with dark matter. According to our best models, clumps of this mysterious substance should have littered the early universe like seeds, each one gathering gas to form a galaxy. The smallest clumps, no heavier than 1 million suns, ought to have spawned dwarf galaxies by the thousands, peppering the cosmos like fireflies around a lantern. Yet when we peer at our galactic neighborhood, we find mere dozens where there should be hundreds. It's as if someone took a cosmic eraser and scrubbed away 90% of these tiny galaxies before they could shine. The culprit, the cosmic web's unforgiving filaments. Picture a delicate sapling trying to grow in a hurricane. In the crowded intersections of the web, where gas flows fast and furious, dwarf galaxies faced a brutal environment. Their faint gravitational pull couldn't compete with the torrents of ionized gas screaming along dark matter highways. Before these fledgling galaxies could coalesce, the web's fierce currents ripped their star-forming fuel away, leaving behind dark matter husks, galactic stillbirths too dim to detect. But the violence didn't stop there. Even dwarfs that managed to form found themselves in a cosmic gauntlet. Larger galaxies, tugged by the web's filaments, would swing past like wrecking balls, their gravity shredding the fragile dwarfs into stellar streams, ghostly ribbons of stars winding through space like tattered flags. The survivors, those lucky enough to form in quieter pockets, far from the web's busiest thoroughfares. This explains why isolated dwarfs, like the oddly pristine Leo T galaxy, still exist. They're the rare few that slip through the web's gravitational sieve. Here's the twist: the missing dwarfs aren't entirely gone. Hypersensitive telescopes like the Vera Rubin Observatory are now spotting their remnants, ultra-faint galaxies with so few stars they're practically transparent, or dark galaxies, where dark matter outweighs visible matter 1,000 to 1. These ghosts of the cosmic web's turbulence are the lost pieces of the puzzle, proof that the dwarfs were there all along, just strangled in their cribs by the universe's invisible scaffolding. So the next time you hear about the Milky Way's modest entourage of dwarf galaxies, remember, their scarcity isn't a flaw in our theories. It's a testament to the web's power, a cosmic filter that decides which galaxies thrive and which fade into the dark. And those silent, dark matter clumps still lurking out there, they're a reminder, even in the vastness of space, no thread of the web lets go easily. The elements that make up our bodies, the carbon in our cells, the oxygen in our lungs, the iron in our blood, didn't originate on Earth. They were forged in the hearts of dying stars, then scattered across the cosmos by explosions so violent they outshone entire galaxies. But here's the astonishing part: those life-giving materials didn't just drift randomly. They hitched rides on the cosmic web's filaments, funneled through space like nutrients coursing through a vast circulatory system. When a massive star reaches the end of its life, it doesn't fade quietly. It detonates as a supernova, blasting its enriched guts into space at nearly 1/10 the speed of light. These stellar fireworks seed the surrounding gas with heavy elements, from the gold in jewelry to the calcium in our bones. But without the cosmic web's architecture, these ingredients might never reach the places where life could bloom. That's because the web's filaments act like interstellar highways, channeling supernova debris along gravity's currents. Imagine tossing glitter into a rushing river. the glitter doesn't vanish, it follows the water's flow, settling in bends and eddies. Supernova remnants behave the same way, carried by the Webb's filaments until they pool in galactic intersections, where new stars and planets form. Evidence of this process is written in the stars themselves. Astronomers studying stellar nurseries have found pockets of gas laced with unusually high concentrations of carbon, oxygen, and even rare earth metals, elements that shouldn't exist in such quantities unless they'd been delivered by multiple generations of supernova. The Orion Nebula, a nearby star-forming region, contains traces of elements that can only be explained if material from dozens of exploded stars had gathered there over eons, guided by the Webb's invisible threads. But the journey doesn't end there. When new stars ignite from this enriched gas, their planets inherit this chemical legacy. Our solar system likely formed in a filaments-dense knot, where generations of supernova debris had accumulated like snowdrifts. Meteorites, ancient fragments of that primordial cloud, still carry traces of radioactive isotopes like aluminum-26, conclusive proof they formed from material contaminated by a near-by stellar explosion. Without the Webb's filaments concentrating these ingredients, Earth might have been born into a sterile void, lacking the elemental diversity needed for life's complex chemistry. And the Webb's role isn't just about delivery, it's about timing. Supernova debris takes millions of years to cool enough to form solid particles like silicates or graphite. The Webb's filaments provide the perfect environment for this process, their vast lengths acting as cosmic mixing bowls where gas can linger, cool, and condense into dust grains. These tiny particles, some no larger than a virus, become the building blocks of planets and eventually the molecules of life. In a very real sense, the sugar in your coffee, the DNA in your cells, even the smartphone in your hand, all began as stardust filtered through the cosmic Webb's labyrinth. So when we look up at the night sky, we're not just seeing distant stars, we're witnessing the universe's grand recycling program, one where the Webb's filaments serve as both conveyor belts and crucibles, ensuring that the ashes of dead stars find new purpose in the birthplaces of worlds. And that means every atom in us, every spark of life, is part of a story written not just in the stars, but in the spaces between them. The cosmic web may be the universe's grandest structure today, but its reign won't last forever. Over trillions of years, dark energy, that mysterious force stretching space itself, will slowly tear this intricate tapestry apart. Picture a spiderweb caught in a hurricane, its threads stretching thinner and thinner until they snap one by one, leaving only tattered fragments fluttering in the wind. That's the fate awaiting our cosmos, a future so distant it defies imagination, yet one we can already glimpse through the laws of physics. Right now, the Webb's filaments are cosmic lifelines, ferrying gas between galaxies and knitting the universe together. But as dark energy accelerates the universe's expansion, those threads will begin to fray. The first casualties will be the longest, most delicate filaments, the bridges spanning the widest voids. Stretched beyond their limits, they'll thin into wispy tendrils, their gravity no longer strong enough to hold onto the galaxies they once nourished. One by one, these connections will sever, leaving galaxy clusters stranded like islands in an ever-widening ocean of nothingness. The Milky Way's local group, a tiny knot of galaxies bound by gravity, will be among the last holdouts. As the space between us and other clusters expands faster than light can traverse it, the rest of the observable universe will vanish from view, swallowed by an impenetrable curtain of darkness. The Andromeda Galaxy, which will eventually merge with the Milky Way in a fiery dance, will become our entire visible cosmos, all other structures redshifted into oblivion. Even the cosmic microwave background, the last whisper of the Big Bang, will fade as its wavelengths stretch into undetectable silence, but the isolation won't stop there. Given enough time, dark energy's grip will reach even into galaxy clusters themselves. Stars on the outer edges of these dwindling islands will find their celestial tethers stretched to the breaking point, flung into the void as their home clusters slowly disintegrate. Eventually, only the most tightly bound systems pairs of galaxies orbiting one another in grim solitude will remain, and then, in a final act of cosmic decay, even those will be ripped apart, their stars scattered like embers from a dying fire. Yet amid this bleak future, there's a haunting beauty. The last surviving stars, dim red dwarfs that burn for trillions of years, will glow in an otherwise lightless universe. Their planets, if any still remain, will float in perpetual night, gazing up at a sky empty of all but a few faint pinpricks. The great galactic cities of today will be reduced to graveyards of black holes and neutron stars, their gravitational waltzes the only motion in an otherwise frozen cosmos. And then, at last, even those will fade as black holes evaporate into Hawking radiation, leaving behind a universe so vast and empty that the cosmic web's existence will seem like nothing more than a fleeting dream. This isn't just speculation. The evidence is written in the redshifts of distant galaxies, the stretching of the CMB, and the relentless march of cosmic acceleration. The web's fate is sealed not by a cataclysm, but by the slow, inexorable unraveling of space itself. And though it will take timescales beyond human comprehension, the lesson is clear. The universe's greatest structures are temporary, woven into existence for just a cosmic moment before darkness claims them forever. Some of the most compelling evidence for the cosmic web's hidden architecture comes from cosmic car crashes, colossal collisions between galaxy clusters so violent they rip the fabric of reality itself. Among these, the Bullet cluster stands out as a smoking gun. Located 3.8 billion light-years away, this system isn't just two clusters merging. It's a forensic snapshot of the universe's dark skeleton laid bare. Here's why: when these clusters slammed together at millions of kilometers per hour, their stars, gas, and dark matter didn't behave the same way. The stars, spaced so far apart they rarely touched, passed through each other like ghosts. The gas, however, piled up in a searing hot knot, glowing in X-rays as it slowed like cars in a traffic jam. But the real shock came when astronomers mapped the mass using gravitational lensing. The bulk of the cluster's gravity, its dark matter, wasn't with the gas or the stars. It had raced ahead, leaving the visible matter in its dust like a shadow detaching from its owner. This eerie separation is the universe's way of showing its cards. Dark matter, unaffected by the electromagnetic forces that make gas particles crash and heat up, feels only gravity's pull. So when clusters collide, their dark matter coasts through unscathed, while ordinary matter gets tangled in the wreckage. The Bullet cluster's dark matter, bullets piercing ahead of the visible debris, proved beyond doubt that the cosmic web's scaffolding isn't just theoretical, it's a physical reality, one we can trace by the gravitational scars it leaves behind. But the Bullet cluster isn't alone. Systems like Able 520 and the Musket Ball cluster reveal similar splits, each collision acting like an X-ray for the universe, exposing dark matter's hidden highways. In some cases, the separation is even more extreme. Clusters like Able 740 show dark matter so far ahead of the gas, it's almost as if the web's filaments are tugging it along like puppeteer's strings. These ghostly echoes from ancient collisions are more than curiosities. They're proof that dark matter isn't just an anchor for galaxies. It's the universe's silent choreographer, guiding the web's growth while remaining forever just out of sight. What's even wilder, these collisions might explain why some filaments appear wispier than simulations predict. When clusters collide, their dark matter doesn't just separate, it stretches, sending tremors down the connecting filaments like plucked guitar strings. Astronomers have spotted faint, warped strands near the Bullet cluster's aftermath, suggesting these cosmic pileups don't just reveal the web, they reshape it. Imagine two towering waterfalls crashing into one another, their spray altering the river's course downstream. That's the scale of disturbance. We're talking about a reshuffling of the cosmic deck that leaves permanent wrinkles in space-time. Yet for all their violence, these collisions are also creators. The smashed gas in systems like the Bullet cluster doesn't just glow, it cools, condenses, and eventually collapses into new stars, seeding the next generation of galaxies. Even the dark matter's path matters. As it surges ahead, its gravity shepherds stray gas into denser pockets, setting the stage for future galactic births. In a way, these wrecks aren't just destructive, they're the universe's way of recycling, of stirring the pot so the web can keep spinning new structures from the chaos. So the next time you hear about a distant cluster collision, remember, you're not just witnessing a cosmic fender bender. You're seeing the cosmic web's secrets spilled across the void, a reminder that even in the darkest corners of space, nothing ever truly hides. The universe always leaves traces. We just have to know where to look. Galaxies aren't just floating adrift in space, they're racing along cosmic superhighways at breathtaking speeds, carried by the relentless pull of the cosmic web's filaments. Picture an interstate system where instead of cars, entire galaxies move in streams, funneled by gravity toward the universe's busiest intersections. The Milky Way isn't a bystander in this grand migration. Right now, we're hurtling through space at over 600 kilometers per second, riding a filament known as the local sheet toward the colossal Virgo cluster, a bustling hub of galaxies so massive its gravity shapes the motion of everything within 100 million light-years. This journey began billions of years ago, when subtle ripples in the early universe's density set the stage for the web's filaments to form. Like rivers carving valleys, gravity drew matter into these channels, creating pathways where galaxies would eventually flow. The Milky Way's filament, the local sheet, is a relatively minor thread compared to the sprawling highways connecting superclusters, but it's our home lane, and it's taking us on a one-way trip toward Virgo's gravitational embrace. Along the way, we're not traveling alone. Neighboring galaxies like Andromeda and Triangulum are moving with us, a celestial caravan streaming toward the same cosmic destination. What's fascinating is how these migrations leave trails. Just as cars on a highway create turbulence, galaxies moving through filaments stir the surrounding gas, leaving behind wakes of heated plasma that glow faintly in X-rays. Telescopes like Chandra have spotted these ghostly trails behind galaxies in the Virgo cluster, confirming that motion along filaments isn't smooth, it's dynamic, even chaotic. Some galaxies get stuck in traffic, orbiting filament intersections for eons before merging with others. Others, like the Milky Way, are still accelerating, caught in a slow-motion free fall toward the cluster's heart. But here's the twist, we're not just passengers on this ride, we're also shaping the highway. The Milky Way's gravity tugs on nearby dwarf galaxies, dragging them into our orbit like a semi-truck creating a slipstream. Over time, this gravitational influence redistributes dark matter along our path, subtly reinforcing the filament we're traveling on. It's a two-way street, the web guides us, and we, in turn, leave our mark on the web. The Virgo cluster itself is a gravitational maelstrom, a tangled knot where dozens of filaments converge. Galaxies there don't just drift, they zip past one another at thousands of kilometers per second, their orbits warped by the cluster's immense dark matter halo. Some, like the giant elliptical galaxy Messier 87, sit near the center, having long ago surrendered to the cluster's pull. Others, like our own local group, are still approaching, destined to merge with Virgo in tens of billions of years. By then, the Milky Way and Andromeda will have already collided, their stars mingling in a fiery dance before plunging into the cluster's crowded core. This cosmic commute isn't unique to our corner of the universe. From the Perseus-Pisces supercluster to the distant Shapley concentration, galaxies everywhere are riding filamentary highways drawn together by gravity's unyielding grip. These journeys aren't random, they're the universe's way of building structure, of concentrating matter into the nodes where galaxies cluster and collide. And just as cities grow where roads intersect, the universe's most massive structures form where filaments meet, their gravity weaving the web ever tighter. So the next time you look up at the night sky, remember, the stars aren't fixed. They're part of a grand, slow-motion river, carrying us toward a destination written in the fabric of space itself. The cosmic web isn't just a map of where things are, it's a script of where they're going, and we're all just following the currents. The cosmic web's vast filaments and voids might be more than just a three-dimensional structure. They could be a shadow cast by hidden dimensions woven into the fabric of spacetime itself. This isn't science fiction, it's a tantalizing possibility emerging from string theory, the boldest attempt in physics to unify all forces of nature. According to this framework, the universe might not have just the four dimensions we experience, three of space and one of time, but up to 10 or 11, curled into shapes so tiny they're imperceptible to us. Yet their influence could be written across the web's grand design, like invisible fingers pressing into the dough of reality. One clue lies in the web's eerily uniform patterns. When astronomers map galaxy distributions, they find filaments and voids arranged in ways that echo mathematical models of higher dimensional geometry. Some string theorists propose that these structures could be projections of brains, short for membranes, floating in a higher dimensional space. Imagine drawing a maze on a sheet of paper, then crumpling it into a ball. From within the paper's two-dimensional world, the maze would appear warped in inexplicable ways. Similarly, our three-dimensional cosmic web might be a distorted shadow of interactions happening in dimensions we can't see. The most radical version of this idea suggests that gravity itself could be leaking into our universe from these extra dimensions. While the other fundamental forces, electromagnetism, the strong and weak nuclear forces, are confined to our brain, gravity might be the only force free to traverse the full higher dimensional space. This could explain why gravity is so weak compared to other forces, and why dark matter's influence seems to follow hidden rules. The web's filaments, shaped by gravity's unseen reach, might be tracing the contours of dimensions we've yet to perceive. But how would these extra dimensions leave fingerprints on the cosmic web? One possibility is through subtle anomalies in gravitational lensing. If higher dimensional geometry warps spacetime in ways general relativity can't fully account for, light bending around massive filaments might carry telltale distortions, tiny kinks in the lensing patterns that betray something deeper at work. Projects like the Euclid Space Telescope are now scanning the web with unprecedented precision, hunting for these minute deviations. Another hint might lie in the web's voids. Some models suggest that extra dimensions could cause space to expand or contract differently in these empty regions, subtly altering the rate of cosmic expansion where gravity's grip is weakest. If voids are growing faster or slower than expected, it might be a sign that hidden dimensions are tugging at the fabric of reality in ways we're only beginning to model. Of course, this remains speculative. No direct evidence proves extra dimensions exist. Yet the cosmic web, with its intricate balance of gravity, dark matter, and dark energy, offers a unique testing ground. If string theory is correct, then the web isn't just a structure, it's a cosmic cipher, its patterns encoding secrets about dimensions beyond our perception. Deciphering it might require rewriting our understanding of reality itself, and that's the thrill. The universe's largest-scale structure could be the very key to unlocking its smallest, most hidden layers. The cosmic web isn't just a network of searing hot plasma and dark matter. Hidden within its filaments lie pockets of cold, dense hydrogen gas, untouched relics from the universe's infancy, waiting to ignite future generations of stars. These reservoirs, some just a few degrees above absolute zero, are the cosmic equivalent of buried treasure fuel so pristine it could power galaxy formation for billions of years to come. For decades, astronomers suspected these cold gas streams existed, but spotting them was like trying to see breath on a freezing night, visible only under the most precise conditions. That all changed when the Atacama Large Millimeter Array, ALMA, turned its razor-sharp gaze toward the web's faintest threads. What ALMA found was revolutionary. Nestled within the Taurus molecular cloud, a filament just 450 light-years away, the telescope detected tendrils of molecular hydrogen so cold they barely emitted heat, just faint whispers of radio waves at specific frequencies. Unlike the superheated plasma found in most filaments, this gas hadn't been stirred by supernova or black hole jets. It was primordial, unchanged since the early universe, a snapshot of the raw material that built the first galaxies. And it wasn't alone. Similar cold streams were soon discovered weaving through the Musca and Orion filaments, their hydrogen molecules clinging together in fragile chains, shielded from disruption by dense cocoons of cosmic dust. The implications are staggering. This cold gas isn't just dormant, it's the universe's emergency fuel reserve. When galaxies exhaust their star-forming material, these filaments act as cosmic pipelines, funneling fresh hydrogen into hungry galactic centers. ALMA observations of the Spiderweb Galaxy, a massive protocluster 11 billion light-years away, captured this process in action. There, cold gas streams spiral inward like icy rivers, feeding a frenzy of star birth at rates 1,000 times faster than the Milky Way. It's proof that the web doesn't just build galaxies, it sustains them, delivering fuel across cosmic time with the precision of a celestial supply chain. But here's the twist: this cold gas shouldn't exist. According to most models, the ultraviolet radiation from the first stars should have fried every last wisp of neutral hydrogen, ionizing it into a diffuse plasma. Yet ALMA data reveals pockets that somehow survived, sheltered in the web's densest filaments like seeds beneath winter snow. One theory suggests magnetic fields played a role, their invisible lines wrapping around the gas like insulating blankets, deflecting destructive radiation. Another posits that the gas cooled and recombined in shadowy recesses of the web, escaping notice until now. Whatever the explanation, these reservoirs force us to reconsider how the universe recycles its building blocks and how much we've overlooked in the spaces between galaxies. The hunt for cold gas is now a cornerstone of astrophysics. Projects like the Next Generation Very Large Array aim to map these streams in unprecedented detail, tracing their flow from void to galaxy cluster. Already, observations hint that the coldest gas isn't randomly scattered. It clusters at filament intersections, drawn there by gravity like dew gathering at a spiderweb's knots. These junctions could be the next frontier of star formation, cosmic crossroads where the universe's quietest, coldest material sparks its brightest fires. And with every new discovery, we're reminded the web's most delicate threads might hold the keys to its grandest transformations. The cosmic web doesn't just connect galaxies, it operates like the universe's most colossal superhighway, a gravitational internet humming with invisible traffic. Picture the filaments not as static threads, but as living conduits pulsing with energy, where galaxies act like nodes in an unfathomably vast network, exchanging information not through light or radio waves, but through the relentless pull of gravity. This interstellar communication happens in slow motion, with every galactic motion, every drift, every collision rippling through the web like a signal across a neural network, altering the paths of surrounding galaxies in an endless cosmic conversation. Think of it this way: if the internet routes data through fiber optic cables, the cosmic web routes influence through spacetime itself. When a massive galaxy cluster tugs on a filament, that gravitational signal propagates at the speed of light, subtly adjusting the orbits of galaxies millions of light-years away. It's not instant messaging. It's a dialogue stretched over eons, where a message sent when dinosaurs roamed Earth might only now be arriving at its destination. Yet despite the glacial pace, the web's efficiency is staggering. Just as the internet's backbone ensures data finds the fastest path, gravity optimizes the web's structure, funneling galaxies toward dense knots and redistributing matter with precision. The parallels go deeper. Like routers amplifying signals, supermassive black holes act as gravity's repeaters, their immense mass reinforcing the web's connective tissue. When two galaxies merge, their central black holes collide, sending gravitational waves, literal ripples in space-time crashing through the filaments. These waves don't just dissipate, they nudge nearby gas clouds, tweak star-forming regions, and even influence the orbits of dwarf galaxies, propagating change across the network. It's a feedback loop on a galactic scale where every event, no matter how localized, leaves a fingerprint on the larger system. But the web's most eerie resemblance to a neural network lies in its structure. Under a microscope, the brain's neurons and their synaptic connections form branching patterns uncannily similar to the universe's filaments and nodes. Both systems optimize for efficiency. Just as neurons cluster to minimize signal delay, galaxies gather where filaments intersect, reducing gravitational latency. Both even have their own versions of dark components. The brain's mysterious glial cells, long thought passive, now known to shape neural activity, much like dark matter shapes cosmic flows. Yet there's one critical difference. While the internet can crash and neurons eventually fade, the cosmic web is a self-repairing network. When voids expand or filaments stretch, gravity compensates, drawing matter back into equilibrium. Collisions don't disrupt the system, they renew it, recycling gas into new stars and weaving fresh threads into the tapestry. This resilience hints at something profound. The universe isn't just a collection of objects. It's a dynamic, self-organizing entity with gravity as its protocol and galaxies as its data, forever transmitting the story of everything. The cosmic web doesn't just shape space, it bends time itself. Nestled within its densest nodes, where galaxy clusters pack the mass of 1 million suns into regions just a few million light-years wide, space-time warps so severely that clocks tick slower here than in the void's emptiness. This isn't science fiction, it's Einstein's general relativity in action, proving gravity's grip stretches far beyond mere attraction. The web's most massive clusters act like cosmic time machines, their gravitational fields so intense they stretch seconds into what feels like eternity for an outside observer. Picture a black hole's infamous time-slowing effect, but on a galactic scale. Near a cluster like the Coma supercluster, where thousands of galaxies orbit a common center of mass, the combined pull of all that matter, plus the invisible halo of dark matter enveloping it, creates a gravitational well deeper than any single object could. Light passing through this region doesn't just bend, it reddens, its wavelength stretched by the cluster's time-dilating influence. Astronomers call this phenomenon gravitational redshift, and it's one of the clearest fingerprints of Einstein's theory etched onto the cosmic web. Here's where it gets even stranger. Time dilation isn't uniform across the web. While a clock at the center of a massive cluster might lag noticeably behind one in an isolated void, the difference isn't static. As galaxies move along filaments, plunging toward clusters or slingshotting around them, their local spacetime curvature fluctuates. Stars orbiting a cluster's core experience time slightly slower than those drifting at the outskirts, a subtle but measurable effect confirmed by precision observations of pulsars, cosmic lighthouses whose ticks are precise enough to reveal these minute distortions. But the web's time-warping power isn't just a curiosity, it's a tool. By measuring how much light from distant quasars redshifts as it traverses clusters, scientists can weigh the web's nodes with unprecedented accuracy. The Bullet Cluster, famous for separating dark matter from visible gas during a collision, also exhibits a telltale time distortion signature. Light that skimmed its dense core during the smash-up arrives at Earth measurably delayed compared to light that took a detour around the cluster's edges. These gravitational time delays act like cosmic scales, letting us weigh the unseen matter warping space-time along our line of sight. What's truly mind-bending is how this connects to the web's evolution. As filaments funnel matter into clusters over billions of years, their deepening gravity wells don't just grow, they actively slow the universe's clock within their grasp. A planet orbiting a star in the Virgo cluster's heart experiences time 5% slower than one floating in the void. Over eons, this adds up. Civilizations born in dense nodes would, from an outsider's perspective, evolve slightly slower than those in the emptiness between. It's a fractal reflection of relativity's most famous thought experiment, twins aging apart but on a scale spanning galactic superstructures, and the Webb's temporal tapestry keeps unraveling surprises. Recent simulations suggest dark energies accelerating expansion might subtly counteract these effects in the far future, stretching spacetime so fast that even the deepest gravitational wells can't fully resist. Time, like everything else in the cosmos, is subject to the Webb's grand dynamics woven not just through space, but through the very fabric of existence. So the next time you check your watch, remember, out there in the darkness between galaxies, time flows differently. The universe isn't just a place, it's a story unfolding at a million different speeds. Dragonfly 44 is the kind of cosmic riddle that keeps astronomers awake at night. Floating in the Coma Cluster's filament, this galaxy spans as much space as the Milky Way but glows with just 1% of the stars. Peer at it through a telescope, and it's nearly invisible, a wisp of light so faint it was only discovered in 2015 when astronomers calibrated their lenses to spot the unspottable. Yet here's what defies logic. Despite its ghostly appearance, Dragonfly 44 weighs as much as our galaxy. The staggering difference, 99.9% of its mass, isn't stars or gas. It's an incomprehensible halo of dark matter, a shadowy shroud so dense it warps the fabric of space around it. This isn't an isolated oddity. Surveys have since uncovered hundreds of these ultra-diffuse galaxies haunting the cosmic web's filaments, each one a cosmic contradiction, vast as giants, dim as dwarfs. Some, like the equally enigmatic Antlia 2, drift through the local group's outskirts with so few stars you could count them individually across a volume larger than the Milky Way's disk. Their dark matter content isn't just high, it's off the charts, up to 10,000 times more concentrated than in normal galaxies. How did they form? The leading theory is a cosmic bait and switch. Early in the universe's history, these galaxies may have been born in unusually quiet pockets of the web where filaments delivered dark matter but little gas. Without enough fuel to ignite prolific star formation, they became celestial deserts, dark matter fortresses with only scattered stellar outposts. But there's a catch. If dark matter alone shaped these ghosts, their stars should be randomly scattered like flour sifted over a table. Instead, many, like Dragonfly 44, show stars clustered in ways that mirror normal galaxies. This suggests something even stranger. Perhaps these aren't failed galaxies at all, but the skeletons of ones that were stripped bare. Simulations reveal a brutal process when small galaxies plunge into dense filaments or cluster cores. Tidal forces can rip away their gas and stars like husks from corn, leaving only the dark matter halo behind. Over billions of years, the remaining stars settle into eerie, expanded orbits, creating the ghostly structures we see today. Yet even this explanation feels incomplete. Some ultra-diffuse galaxies float in isolation, far from the gravitational slaughterhouses of clusters, their dark matter untouched but their starlight still absurdly faint. The real puzzle isn't just their formation, it's their survival. With so few stars, these galaxies should be catastrophically unstable, their sparse stellar populations flung apart by random motions. Yet they persist, held together by dark matter's vise grip. Some even host globular clusters, dense knots of ancient stars that typically orbit much brighter galaxies. This hints at a turbulent past where these ghosts were once something grander, their current state just a phase in a billion-year metamorphosis. What's most haunting is what these phantoms imply about the web itself. They're living proof that dark matter doesn't just sculpt the universe's structure, it can dominate it entirely, spinning out galaxies where the ordinary matter we see is little more than a footnote. And they're not relics. New ones may still be forming as the web's filaments channel dark matter into ever denser streams, setting the stage for a future where ghost galaxies outnumber the bright ones. So the next time you gaze at the night sky, remember, for every glittering spiral like the Milky Way, there could be 100 shadows just like dragonfly 44 dark doppelgangers hiding in plain sight, whispering secrets about the web's invisible hands. Before the cosmic web's filaments took shape, before the first stars flickered to life, the infant universe was a roiling sea of sound, a symphony of pressure waves crashing through a superheated plasma. These weren't ordinary sound waves. They were Baryan acoustic oscillations, primordial ripples so powerful they left permanent scars in the fabric of space, echoes that still resonate in the web's architecture today. Imagine dropping a stone into a pond, except here the pond is the entire cosmos, and the ripples freeze mid-motion, etching their pattern into the distribution of galaxies for eternity. Here's how it happened. In the universe's first 300,000 years, matter wasn't yet neutral atoms. It was a searing plasma of protons, electrons, and light, all crammed together so tightly that photons couldn't travel far without colliding. But dark matter, unaffected by this electromagnetic chaos, was already clumping under gravity's pull. The ordinary matter, however, was trapped in a tug-of-war. Gravity tried to compress it, while the intense radiation pressure from photons pushed back, creating oscillations, sound waves, that raced outward at half the speed of light. These waves carried Baryan's ordinary matter like surfers on a tsunami, piling them up at the edges of expanding spherical shells. Then, the universe hit a cosmic snooze button, recombination. As space cooled, protons and electrons finally combined to form neutral hydrogen, freeing photons to stream away as the cosmic microwave background. Suddenly, the Baryan photon fluid vanished, and the sound waves stopped, freezing the Baryans in place at precise distances from their origins. The result, a universe stamped with a cosmic ruler, peaks of matter density separated by roughly 500 million light-years, the wavelength of those primordial sound waves at the moment they froze. Today, we see that ruler everywhere. Galaxy surveys like the Sloan Digital Sky Survey reveal galaxies clustering at those exact intervals, a statistical fingerprint of the ancient oscillations. It's as if the universe took a snapshot of its own sound waves and pasted them into the cosmic web's blueprint. The most stunning confirmation came when astronomers compared these galaxy distributions to the cosmic microwave background's temperature fluctuations. The match was uncanny. The CMB's hot and cold spots aligned perfectly with the web's over and under dense regions, proving they shared the same acoustic origin. What's wild is that these oscillations weren't just a one-time event. They set the tempo for structure formation. The frozen ripples became gravitational seeds, with slightly denser regions attracting more dark matter and gas, eventually growing into the filaments and nodes we see today. Even now, the web's largest voids, those vast, empty bubbles, often span the same 500 million light-year scale, their sizes echoing the original sound waves like cosmic drum heads still vibrating from the Big Bang's strike. But here's the twist: these oscillations aren't just fossils, they're tools. By measuring the precise spacing between galaxy clusters, astronomers can track how dark energy has stretched the universe over time. The frozen sound waves act as a standard ruler, letting us measure cosmic expansion with unprecedented precision. It's like finding a tape measure baked into the universe's DNA, one that reveals not just the web's structure, but the very forces that shaped it. So the next time you see a map of the cosmic web's sprawling filaments, listen closely. Hidden in its geometry is a rhythm, a ghostly echo of the universe's first and only symphony. The music stopped long ago, but its score remains, written in galaxies and voids. A reminder that even in silence, the cosmos never forgets a vibration. For billions of years after the Big Bang, the universe was a featureless void, no stars, no galaxies, just an endless sea of hydrogen fog so thick it swallowed light whole. This was the cosmic dark ages, an era when the cosmic web existed only as invisible tendrils of dark matter, waiting for something to ignite. Then, around 200 million years after creation, the first sparks flickered in the darkness. Pinpricks of ultraviolet radiation began punching holes in the hydrogen curtain, clearing bubbles of transparency that grew, merged, and ultimately flooded the cosmos with light. This was cosmic dawn, the moment the web stopped being a ghostly scaffold and became a canvas for the universe's first masterpieces. The James Webb Space Telescope has revolutionized our understanding of this epoch. Peering back over 13 billion years, its infrared eyes have captured galaxies so young they shouldn't exist, clusters of stars blazing just 280 million years after the Big Bang. These aren't the frail, fledgling systems astronomers expected. They're monsters, some already weighing billions of suns, their light warped and magnified by the cosmic web's filaments like jewels on a spider's thread. How did they grow so fast? The answer lies in the web's unique physics. Dark matter's filaments funneled gas into dense knots with terrifying efficiency, compressing hydrogen into star-forming factories that operated at speeds inconceivable today. One of Webb's most shocking discoveries is GNZ 11, a galaxy so distant we see it as it was just 400 million years after the universe began. It's producing stars 20 times faster than the Milky Way, a frenzy of creation powered by pristine gas streaming along the web's filaments. But here's what's truly staggering: GNZ 11 is surrounded by a vast bubble of ionized hydrogen, clear evidence that its ultraviolet radiation is already reshaping the cosmic web around it. This single galaxy, barely a cosmic toddler, is carving its own niche in the universe, proving that the first stars didn't just light up the dark, they rewrote the rules of structure itself. The process wasn't gentle. As more galaxies ignited, their radiation blasted through neighboring filaments, heating the gas and suppressing star formation in smaller clumps. This created a cosmic hierarchy. Massive galaxies thrived at filament intersections, while their smaller siblings starved in the shadows. Simulations suggest this feedback loop, where galaxies altered the very web that birthed them, set the stage for the universe we see today. Without it, galaxies might have remained small and numerous, dotting space like fireflies rather than gathering into the glittering metropolises of the modern cosmos. Webb's data reveals another surprise. These early galaxies aren't scattered randomly. They're already arranged along faint protofilaments, visible as ruby-red smudges aligned like beads on a string. This means the cosmic web's architecture was guiding galaxy formation from the very beginning, its dark matter skeleton shaping the universe's destiny long before the first stars even flickered to life. And there's a haunting beauty to it. The same filaments that now feed mature galaxies once cradled their ancestors, a celestial inheritance spanning billions of years. Yet for all we've learned, cosmic dawn remains shrouded in mystery. Webb's latest images hint at galaxies even older than GNZ 11, their light attenuated to near invisibility by the thickening hydrogen fog of the dark ages. Some theorists suggest the very first star's population, 3 stars, made purely of hydrogen and helium, might still hide in these shadows, too dim for even Webb to spot. Others believe these primordial giants died long ago, their supernova seeding the web's filaments with the first heavy elements, the building blocks of everything from planets to people. What's undeniable is how transformative this era was. In just a few 100 million years, a blink in cosmic time, the web went from a silent scaffold to a vibrant network, its filaments thrumming with starlight. And as Webb peers deeper, we're witnessing the dawn not just of galaxies, but of the interconnected universe we call home, a place where light, matter, and gravity dance to a rhythm first set in the darkness. Could the cosmic web be a single thread in a vast, unimaginable tapestry, a tiny fragment of something far larger than our universe. Some physicists speculate that the patterns we see, the filaments, voids, and vast galactic clusters, might not be unique to our cosmos. Instead, they could be echoes of a deeper structure, one where the web we call home is just one version among countless others, each woven into its own distinct reality. This isn't pure fantasy. The mathematics behind cosmic inflation, the theory that our universe expanded exponentially in its first moments, suggests that if inflation happened once, it could have happened infinitely, spawning bubble universes beyond our own. Each of these bubbles would have its own laws of physics, its own version of matter, even its own cosmic web. And while we can't see these parallel universes directly, the patterns in our own might hold clues. The web's filaments, for instance, resemble structures predicted by quantum field theory, the same math that allows for the possibility of multiple coexisting realities. It's as if the universe left breadcrumbs in its design, hinting at connections we're only beginning to trace. Consider the cold spots in the cosmic microwave background, regions of unexpected chill that defy standard explanations. One controversial theory suggests these could be bruises where our universe once brushed against another, their gravitational pull subtly warping our own cosmic web. The idea remains speculative, but if true, it would mean the web isn't just a local phenomenon, it's part of a multiversal network, each strand potentially tethered to realities beyond our own. Even more tantalizing is the way dark matter behaves. Its distribution along filaments is eerily precise, as if guided by forces beyond gravity alone. Could this invisible scaffolding be shaped by influences leaking in from adjacent universes? Some models of string theory propose that higher dimensions, realms beyond our four-dimensional spacetime, might allow for interactions between parallel worlds, their gravity seeping through like water through a sieve. If so, the web's most puzzling features, its unexplained voids, its oddly uniform structure, might not be random at all, but the result of a conversation happening across the fabric of reality itself. Of course, this is the frontier of cosmology, where evidence is scarce and speculation runs wild. But the very fact that we can ask these questions, that the cosmic web's patterns invite such daring possibilities, speaks to its profound mystery. Whether or not other universes exist, the web reminds us that reality is far stranger than we once imagined. Its filaments may bind more than galaxies. They could be threads in a tapestry too vast to comprehend, connecting us to worlds beyond sight, beyond time, beyond even the limits of our imagination. The cosmic web has revealed countless wonders, but for every answer it offers, a dozen mysteries remain tangled in its filaments, one of the most baffling. Its unexpected lumpiness. Despite our most advanced simulations, the universe's large-scale structure is far clumpier than predicted, with galaxies gathering in dense knots and sprawling voids far larger than math says they should be. Imagine shaking a box of glitter, only to find it clumped in bizarre, asymmetrical patterns instead of scattering evenly. That's the puzzle astronomers face, except the glitter is galaxies and the box is the observable universe. Some blame dark matter's quirks. If this mysterious substance interacts with itself in ways we haven't yet detected, perhaps through some exotic force beyond gravity, it could explain why filaments seem to braid into thicker strands in some regions while fraying into gossamer threads in others. Others point to dark energy's accelerating push, arguing that its influence might stretch voids faster than models account for, leaving matter bunched up like rush-hour traffic squeezed into fewer lanes. Then there's the wild card, primordial magnetic fields. These hypothetical relics from the universe's first second could have twisted gas flows like invisible fingers, sculpting the web's irregularities before galaxies even formed. But the anomalies don't stop there. Certain filaments appear to spin slowly, an eerie phenomenon with no clear explanation, since cosmic structures shouldn't rotate on such vast scales. Could this be evidence of undiscovered forces, or even vestiges of higher dimensions warping spacetime at distances we're only beginning to measure? Even the Webb's missing dwarf galaxies, fewer in number than simulations predict, hint at gaps in our understanding of how dark matter orchestrates cosmic growth. The next generation of telescopes aims to crack these enigmas. The Vera Rubin Observatory's decade-long legacy survey of space and time will map billions of galaxies, tracing the Webb's finer threads with unprecedented detail. Meanwhile, the European Space Agency's Euclid mission will hunt for distortions in spacetime caused by dark matter's grip, while NASA's and Nancy Grace Roman Space Telescope peers into the Webb's darkest corners with infrared eyes. Together, they'll test whether Einstein's gravity holds true across cosmic scales, or if the Webb's oddities demand new physics altogether. Perhaps the most tantalizing question isn't about the Webb's structure, but its origins. Those faint whispers of the cosmic microwave background, the ones that seeded the Webb's growth, were they truly random quantum fluctuations, or could they bear fingerprints of something deeper? Some theorists speculate they might encode clues about the universe's birth, even hints of a multiverse. Until we know, the cosmic web remains both a map and a riddle, a reminder that the universe's grandest design is still whispering its secrets, waiting for us to listen. From the invisible scaffolding of dark matter to the searing hot rivers of gas between galaxies, the cosmic web isn't just a structure. It's the universe's greatest storyteller. Over these 30 revelations, we've traced its filaments like detectives following clues, uncovering how it shapes star birth, fuels black holes, and even bends the flow of time itself. Think of everything we've explored: ghostly dwarf galaxies clinging to dark matter threads, supermassive black holes lurking at filament intersections like cosmic spiders, and primordial sound waves frozen into the Webb's very fabric. Every atom in your body, every star in the sky, is part of this grand network, a tapestry woven over billions of years, where even the emptiest voids play a role in sculpting reality. But here's what's truly humbling: for all we've uncovered, the Webb's deepest secrets are still unraveling, those unexplained spins in distant filaments. The eerie synchronization of galaxy clusters across billions of light years, they're proof that the cosmos still holds cards close to its chest. Maybe the answers lie in higher dimensions, or quantum entanglement written across galactic scales. Or perhaps, as telescopes like Euclid and the Vera Rubin Observatory peer deeper, we'll find entirely new rules governing this celestial labyrinth. That's the beauty of the cosmic web. It doesn't just connect galaxies. It links ideas, bridging the infinitesimal quantum world to the vast stretches of spacetime. It ties humanity's thirst for understanding to the universe's endless creativity. So tell us, which secret left you awestruck? Was it the dark matter rivers guiding galaxies, the universe spanning magnetism, or the haunting possibility that we're just one thread in a multiversal tapestry? Drop a comment below. We're obsessed with these mysteries too, and if you're craving more cosmic revelations, hit subscribe. The universe has infinite stories left to tell, and we're just